In last two lectures, we learned about the snake oil method, and the main purpose, or rather main aim of such a method, was that you could use this to prove identities, combinatorial identities, without actually evaluating them. Okay, so you
Yes.
start with some particular identity, you manipulate this identity and make the so to say, the terms of this particular identity as coefficients as a of a
Yeah.
generating function.
Okay.
And
Excuse me,
then,
ma'am. Agilan texted me and said that he will not be able to come today.
okay,
Yeah.
and then with that generating function, we do manipulations and find the coefficients which are exactly the identity which you wanted to prove. Okay,
Yes.
so that was the snake oil method, which we saw was applicable in quite a lot of places. A huge class of identities could be proved using that. Okay,
Mm.
so, and in particular, like whenever the coefficients were giving rise to hypergeometric series, then we were able to do it. Okay,
Yes.
now what is the need of?
We also did it for not hypergeometric things by considering the EGF.
True,
Like,
true,
yeah.
true. So most of the examples which we saw is what I said were being when we applied the snake oil method on the hypergeometric series. Okay. What
Yes.
happens in today's time is that computers can find proofs of these combinatorial identities. And most of the ones which we did by snake oil method in earlier can be solved using the computer. Okay. And
Oh,
here in this particular section, we'll actually see how that is done. So it is in some sense a way of saying what you did earlier manually can actually be done through computer. But for that thing to be fed to a computer, you have to figure out or make it simple enough that it could be fed to computer, right?
okay. Yeah.
However, this doesn't really mean that whatever we did was a waste. That was the starting of it. You got hold of it, you understood how things work, and now we will see how it can be made into an algorithm which will ultimately be fed to computer that can give you a proof for the identity which you are working with. Okay.
Okay.
However, not every example which can be solved using snake oil method can be handled through this new approach. So we really try to see what works.
Okay.
And in that, let's say the identity that you want to prove is this, that some particular summation is some function of n.
Okay.
Okay. And this you want to prove that it holds true for every n greater than equal to 0.
Okay.
So then a rough recipe for doing what we are going to do is that you divide this particular sum by this function,
Okay.
so that then this is something which is not depending on n. Earlier the right hand side was dependent
Yes.
on n. Now after I have divided each unk by this function, I have a new function fnk, and now the summation of fnk over k is
One.
independent of n.
It will be one. Yes.
Yeah, it becomes one. That is one thing. Even if it was not one, if let's say this happened to be some 2n, let's say as a function, and you would divide by just the n here, so even the 2 here does not harm me, does not
Yes.
create a
Okay.
problem for me. We'll see in a moment why. But more important part is that the now right hand side of this particular identity, so proving this is equivalent to proving this.
Yes.
But here, what advantage I have is that right hand side does not depend on the variable n. Okay, so I want to make use of this. Now, since this summation runs over all the values of k, I could take the, I could start with f of n k plus 1 and then sum it over k, and still will get the answer 1.
Yes.
Or if I keep it k and sum over k, still I will get the answer 1. Right?
Yes.
But now the benefit from this, what I get is that this summation now is 0. Because since this particular summation evaluates to 1 and summation of f and k over k is also evaluating to 1,
Oh, yeah.
the
Right.
difference is 0.
Yes.
So this is what we want to make use of. And now you see why I said that this being 1 or 2 does not make a difference. As long as this is some constant, I am okay with it.
Yeah, it will
Because the
cancel and
same,
make it 0.
exactly. So equation 2 comes from 1 regardless of whether this is 1 or any other constant.
Right.
Right? Now, if let's say if at all we are lucky enough so that there is some function g, so now this is a, like, it's a huge summation of difference of terms. If you want to reduce it further, one technique which we have learned earlier is that the terms should in some sense cancel out with each other, which you also call as telescoping the sum.
Yes.
Right? And when can that happen? The terms from this and terms from this mainly have things in common, or this particular summation, or rather this particular difference leaves out things which gets cancelled with the next value of k.
Yes.
Right? So suppose you have a function g which satisfies this equation, that f of n plus 1 k minus f of nk, which is this inside summand, is equal to the difference of the function evaluated at nk plus 1 and nk. So if this happens to be true, then it is clear to see that if I take this particular summation on the range minus L to positive k, then this will survive only for g n capital K plus 1, and the bottommost term here would be gn minus L. Right?
Yes.
All in between terms will cancel out consecutively.
Right.
So we have reduced the equation, this entire equation, to just this, provided I have such a function g. Right?
Yes.
So since we are assuming such a g, suppose we further assume that this particular function g, for the values when like limit small k tends to plus or minus infinity, this function becomes 0, then you would actually see that this will be 0 for high values of k, this will also be 0 for high values of k. So they individually being 0, so this entire thing is also 0, which means you would have proved this,
Yes. Okay.
which means you would have proved this,
Yes.
which then means that you would have proved the original identity which you started with.
Okay.
Right? So far with me?
Yes.
Great. Now we move further and see what all we have assumed and for how long can we keep it. So this is the Wilf-Zillberger's theorem. What is happening at your side? A lot of noise.
Oh, is it fine now?
Yeah.
Sorry. Yeah.
So Wilf-Zillberger's theorem, which is why it's also WZ.
Okay.
Okay. You see the main title of today's lecture, WZ pairs. So some particular pairs that we are going to deal with. The pair consists of the function f and the out of the box function g. Okay, we'll slowly develop how this g can be evaluated, etc. But currently I know that if I can get hold of f and g, which satisfies this and these conditions, the boundary conditions, that then I'm done.
Yes.
Correct? So suppose let fg, a pair fg, satisfy fn plus 1 k minus fn k equal to gn k plus 1 minus gn k. And suppose that the limit of this particular function as k tends to plus or minus infinity is 0 for all the values of n, then summation k, summation over k of fnk is a constant. Then this particular identity holds true for every n non-negative. So
Okay.
this is the theorem which Wilf and Zillberger proved. So this, as it is theoretical, right? It just says that as long as you have a function f and a function g which satisfies this, further g has to satisfy this, then what can you say about f is this for every value of n?
Okay.
Okay, so we see this on a very small example, which if you just see this as it is, you will see, oh, why you are even dealing with this. I have much better and quicker proofs to handle this
Yes.
one.
Mm.
But let's just start with the smallest possible. So then what would you have your f of nk to be?
F of n case this n choose k.
Hmm? That's it.
No, yeah, f
So
of
what
n.
is unk in this? So let's just see this once.
Oh, it's the sum over all k's. So it will be uh, for k, it will, so for k, the kth term will be n factorial. So the whole thing is n factorial by n k factorial times n minus k factorial.
No, as it is, if this is what is given to you and you want to put it in the machinery that we have seen, what is UNK in this identity?
Oh, yeah, UNK is the whole sum on the LHS. So UN as a function of nk, it will be n choose k.
Okay. And what is RHS of N?
RHS of n is a function of n, which is 2 to the power n.
Right. So then the function capital F of NK is what?
Capital F of nk will be n choose k divided by 2 to the divided by 2 to the power n. The
Great.
sum, yeah. Uh,
So F and K is N choose K divided by 2 raised to N. Okay.
yes.
So to work this thing out, I would want a G and K. So let me just sneakily tell you that I am going to choose this particular function as my G and K. So I'm choosing, so this is small k, okay. So G and K is minus of N choose K minus 1 divided by 2 raised to N plus 1. Okay. Now, once this comes in front of me, I have a few questions. Does this G really work? Which means, does this G satisfy this particular
Limit.
equation? Does this satisfy this equation? Only then I would know that this particular function summation is a constant number, right?
Yes.
So let's just check. So you have f of n plus 1 k minus fn k equals gn k plus 1 minus gn k. This is what you have to verify. So left hand side is 1 upon 2 raised to n plus 1, n plus 1 choose k minus 1 upon 2 raised to n and choose k. Correct?
Yes.
So you evaluate this and you come down to this. So after some steps, you get that it is n factorial times 2k minus n minus 1 divided by 2 raised to n plus 1 k factorial n minus k plus 1 factorial. Similarly, I come to this and attack this with this
Minus
as the
n choose k
substitute.
minus n.
Okay. And get that after evaluation that this is also n factorial 2k minus n minus 1 over 2 raised to n plus 1 k factorial over n minus k plus 1 factorial. So both of these terms match up. So at least what f and g are given to me satisfies this particular equation.
Okay. Yes.
Next thing is to check this.
Yes.
Whether the limit of g and k as k tends to plus infinity or minus infinity is 0 for every n which is non-negative. So if you take any particular n which is non-negative here and take k to go to plus infinity, what is that evaluates to?
0.
0. Why?
We had seen that question where for which of the values of
Right.
k it will be 0,
So
and
as soon as k minus 1 is larger than n,
yeah, it
the
becomes 0.
binomial coefficient is 0. Therefore, g and k as k tends to plus infinity is 0. Now, what happens if k is tending to minus infinity?
Same, 0.
And again, the same reason that this evaluates to a non-zero value if and only if k minus 1 is in between 0 and n both inclusive,
Yes.
right? So g and k is 0 for k approaching to plus or minus infinity. Therefore, all the hypotheses of the WZ theorem are satisfied, and hence you know that this is a constant.
Constant.
So we have seen the application of that theorem. But what is more boggling the mind is, where did this g come from? Here,
Ma'am, we know that f will be a constant, but we don't know that it will be 1, I think. Do we?
no, we don't as of now. That would need
But
some
to
extra, so to say, computation, but that
no,
is
but
what
to
we had
prove
up.
that the identity holds, don't we need to show that that constant is 1?
Yeah, so wait for a while. There is
Okay,
more
okay.
to this particular method.
Okay, yeah.
Okay, so what we have done is just to see the application of this particular theorem. So from this theorem, we have so far arrived at the conclusion that the summation k fn k is a constant. We have not yet arrived to the place that summation of this thing is actually 2 raised to n. No, I am not claiming that. We're just saying that summation of n choose k divided by 2 raised to n is some constant. That is what we have arrived at.
Okay.
Okay. Now, coming further, you did all this when I gave you a g. But what happens if I don't have a g? Or if you don't have a g or you don't know how to find this g? then we are stuck. So now we see how to really come up with this G, or what are the um, tricks which helps us find such a G which works for us. Okay. So first of all, it has to be of the form Rnk times Fn k minus 1. For almost all the class of identities that we deal with, the function g and k looks like the product of two functions Rnk and Fnk minus 1. Fnk minus 1 you already know, right?
Yes.
And this Rnk, you know, is a rational function of n and k.
Okay.
But again, now you have introduced a new R, but how to come up with this R? That
Right.
is the next question, which will be answered later.
Okay.
So since F comes from the given question itself, need not worry about F, so we worry only about the R. The class of identities for which the above simplification is true, which means this entire simplification of assuming things that something something vanish and something something turns out to be this, etc., is true. For the class for which it is true is the class of those that are of the form summation k, summation over k, f and k is equal to 1, in which the function f has the property that both of these ratios are rational functions of n and k.
Okay.
Okay, and now you are coming to what was your doubt, that we have only shown this to be a constant and not really a 1.
Yeah.
Proceeding further along the same lines, so let's just call some pair fg to be a wz pair if it certifies this particular equation
Okay.
and it satisfies this difference to be equal and the boundary condition for g to hold. Okay, if these three conditions are satisfied, then you call fg a wz pair. So clearly, if some pair is a wz pair for some given equation, then it shows that this particular fg proves that identity, right? Certifying this automatically means that.
Yeah.
So let's see the recipe for solving identities using wz pairs. What it, so, I mean, it's more or less the recap of what we did. Given something like this and a rational proof certificate R and K, okay?
Okay.
So far I said something, something, something. You come up with a G and do the rest of the things. And then we said that we need to worry only about R. So now I'm saying that if you have this particular identity and you also have a rational
Certificate.
proof certificate RNK, then FNK has to be obtained by dividing UNK by the RHS of N, and
Yes.
GNK has to be defined by the product of RNK and the FNK. RNK is given to you, FNK
Okay.
you have computed. So now you have both F and G, right? So rest of the steps, what it says is just check that F and G is a WZ pair.
Okay. Yes.
Okay. Equation 3 is this. Equation 4 is this.
Okay.
So certifying, so checking that both of these holds, and this automatically is true because you have defined your FNK to be this, right? So checking if 3 and 4 holds, this together with this definition of FNK itself, you would know that FG is a WZ pair.
Yes. Okay.
Okay. And as extra precaution, you should always check the identity for n equal to 0,
Okay.
because that is where things go wrong mostly.
Oh, okay.
Okay, so if I start with, let's say, this particular summation over k of minus 1 raised to k, n choose k, 2k choose k, 4 raised to n minus k equals 2n choose n. So what is my u of, so you see this equation again, this is sum summation of u n k over k equals RHS of n. So comparing it with this, what is your uk of n, u of kn?
For this LHS.
Is it the whole full LHS or the summand?
No, the thing in the sigma -1 to the power k, n choose k, 2k choose k, and 4 to the power n minus k. That part.
Right. So the summand is u and k. What is the RHS of n?
2n choose n.
Right. So then the FNK and RNK is given to be 2k minus 1 divided by 2n plus 1.
Okay.
Okay. So this is
Then
that rational proof certificate.
yeah. So then we need to find f of n comma k minus 1.
Right. So first of all, what is f of nk? It is
This
this
divided by
summand
2n choose n.
divided
Yeah.
by 2n choose n, which is this.
Hmm.
And then GNK is this thing evaluated at k equals k minus 1 and producted
Times
with this.
the certificate.
Right. So that gives me minus 1 raised to k, 2k minus 1 over 2n plus 1, and then rest of it at k minus 1. Oh, this should have been a k minus 1 here. Sorry,
Yeah.
it's a
Hmm.
typo. So n choose k minus 1, 2k minus 2 choose k
K
minus 1,
minus 1.
4 raised to n minus k plus 1 over 2n choose n.
Yes.
Okay. So now I leave this as an exercise for you to check that f and g here, they satisfy equation 3 and 4.
Okay.
What was
Yeah.
equation 3?
3 was the difference of
Right.
if, yeah, and 4 was the boundary conditions limit.
Yeah.
K
So
tends to
checking
0.
4 is actually pretty easy and
Yeah,
quick because all the things
they will become
involved.
0. Yeah, k tends to
Right.
infinity.
So that is fine. And the rest of it, you also check for n equals 0. And then once you are done with this, you would know that this identity is true
Yes.
because of this entire recipe of the WZ pairs. Okay.
Yes.
Well, now coming back to square one, how to find this RNK? You
Yeah.
could do this entire business if you were given with this rational proof certificate function R. But what if that is not given? How do you really find this R? Or equivalently, how do you find this function G? So, first of all, start observing that since f and k is always known as soon as the identity is given to you, this particular difference is also known. You can compute it.
Yes. Yes.
But this function does not really make a so if this difference I call as f of nk, then what I really want is that the function g should be such that f of nk is equal to g of nk plus 1 minus g of nk, right?
Right.
But notice something here, that this particular function is a function of two variables, n and k. This is also depends on, this also takes all these three elements here. All of these take n and k as inputs, right? Here k plus 1, here k. But n remains same for all of them. So n does not really change, correct? For different values of k,
Yes.
only k would change here,
K
n would not
changes.
change. So n is working as a silent parameter. It does not change in the entire equation. So writing this entire thing as f as a function of two variables, this could actually be written as a function of single variable. So
Yes.
this f and k I would then write as f of
FK.
k, and this I would write as g of k plus 1, and this then is g of k.
K.
So then what we are actually saying is that given such an fk, remember that this we know already, right? This is nothing but this f and k, which is this difference. And this difference we know because we know f and k.
Yes.
So what we're really saying is that, can we find a function g depending on k such that f of k is g of k plus 1 minus g of k, right? Just
Okay.
translating
Yeah.
it as it is.
Hmm.
However, if I define my g2 to be f1, g3 to be f1 plus f2, and so on till gk is defined as f1, f2, and so on till fk minus 1. So then gk plus 1 will be summation f1, f2 up till fk.
Yes.
However, this will be the summation till fk minus
K
1.
minus 1.
So then this difference is left out to be just fk.
FK.
So this is something weird then,
Yes.
because something which we are trying to find with so much difficulty seems to be readily available, and that too always, right?
Yes. Right.
So this is not going to do the job for me. So let's see what is really missing. So before that, let's say a function fk
No.
of
Why won't it be doing the job? I didn't understand that part.
that becomes triviality.
Oh. Oh. Okay. Hmm.
You just rewrote your fk as fk.
Oh.
You
Oh.
did
It's
not
the
get
same
new
thing.
function anything.
Oh. Yes. Yes. Hmm.
Yeah. So now let's see a definition. So some function fk of integer k is a hypergeometric term if the ratio of consecutive terms is a rational function of k.
Okay.
And some examples of this are, let's say, k factorial. So then f of k plus 1 is going to be k plus 1 factorial. Fk is going to be k factorial. So f of k plus 1 over fk is going to
K
be
plus 1.
k plus 1. Similarly, so this k plus 1 actually turned out to be a polynomial.
Rational
Forget
function.
about
Yes.
rational,
Yes. Yes.
much stronger. However, if you choose this, then what you're going to get is a rational function, like a
Rational.
proper rational function. Even if you choose this is going to give you a rational function. However, if you take this, it is not going to give you a rational function. Why? Because
K
k
plus 1
plus
to the power k plus 1 divided by k to the power k is not a rational function of k.
right. And similarly for the exponents of this type.
Yes.
What can you say about this particular function as fk? Summation of, first of all, this, whenever you are dealing with the binomial coefficients, most of the binomial coefficients turn out to be hypergeometric terms.
Okay.
For this very reason that they ultimately look something of this type. In numerator, you will have some factorial. In denominator, you'll have some factorial. And then with the consecutive terms, only one or two terms are left out, rest everything cancels. Okay. So that contains a huge class of hypergeometric terms.
Okay.
And what I was saying is, so this particular function fk, which I showed at the bottom. So what can you say about this fk? Is this going to be a hypergeometric term or not?
I think it will be.
Yeah, but thinking does not work. So you
Yeah,
have to
the
actually
binomial,
sit
the
down and check.
sum. Yeah. Okay.
So as of now, it does not reveal itself whether it is going to be a hypergeometric term. Doesn't it either say if it is not going to be a hypergeometric term, right? So neither side is obvious. We
Right.
feel that, this is going to be the case, but we'll have to actually sit down and work on this to see whether it is actually hypergeometric or not. So the correct question we should have asked for the existence of GK was that, does there exist a hypergeometric term GK such that f of k is GK plus 1 minus GK for all the integers k?
Okay.
Okay. So, oh, sorry, it's already written here. So the correct question is actually asking for a hypergeometric term GK, not just any function GK, such that f of k can be written as difference of GK plus 1 and GK. And this particular thing can be done using the algorithm which is developed by Gosper in his paper titled Decision Procedures for Indefinite Hypergeometric Summations.
Okay.
What this algorithm does is that you input an f to it. So this particular fk, you pass it on as an input. And what it returns is either a hypergeometric term gk, which works, which means a hypergeometric term function gk, such that f of k is gk plus 1 minus gk, or it says that for sure there is no such function which
Okay.
works. It will never come back saying, I do not know or I could not find in my database. It gives you a definite answer whether there is a hypergeometric term which works, in which case it comes back with the function itself, or guarantees you that there is no such function. Okay. So with
Okay.
this entire setup, what we have done is that we have found a GK, or we know that this particular method fails down.
Yeah.
Okay. So if GK exists, GK comes out from the algorithm, and then you know the function G, and then you have to check whether FG is a WZ pair to prove the identity. And since this entire theory is developed for the cases, so this entire thing is developed for the case when summation of k f and k is equal to 1, you know that the identity exactly holds and it is not going to give you just some constant value here. Okay, so there are how to say, there are steps in the method itself, but once you know the full method, it is simply saying that, so there are these shortcuts that you don't have to look for the constant here, but you know that it is particularly 1.
Okay.
Okay. So this is it. And this ends the lecture and the
Okay.
course. Any
Mhm.
questions? Good luck for NSEM.
Thank you.
Yeah, any questions?
No, I'm good for now.
Okay, so I have already announced on the Moodle, you people might have already seen. The first part happens on 28th.
Yeah. Yes.
Okay. Second part, so I will leave it open for 3 days.
Okay. Yeah.
Yeah. And the second part will happen on 3rd
Third.
of January. Okay.
Okay. Yes.
7 p.m. IST, 1 hour.
Okay. Okay.
And then maybe I'll give you some extra time to scan and send it to me.
Okay.
Yeah.
Yes.
Okay then. Good luck.
Yeah. Thank you.
Okay.
Okay.
I'll end the meeting then.
Yeah. Yeah. Okay.